So for your class, you're going to have to both understand the conceptual basis of the photoelectric effect, as well as how to apply the photoelectric effect to a problem. So this video will cover both of those two things. All right, so the first thing, what is the photoelectric effect anyway? Well, basically, the photoelectric effect involves a sheet of metal, and so that's essentially what this is right here. And what you're doing to the metal is shining light. So suppose you shine light onto the metal, and here I show you in red light, and I'll call it electromagnetic radiation, so EMR, right? As the light is being shown onto the metal, what happens is the light transfers energy. And the energy, if you remember from Planck's equation, is equal to h times nu. So what happens is as the light transfers energy to the metal, these electrons start getting excited. So they start moving. All right? And the more energy that's transferred to this metal, the faster the electrons start moving. Eventually, the electrons have so much energy that they can get ejected. All right? And so this is called photoelectric emission. And that's to say the emission of a photoelectron from a metal surface. Now, conceptually, you should know that the photoelectric effect supports the particle theory of light. Remember, there's the idea of particle-wave duality, where light can behave both as a particle and a wave. The photoelectric effect supports the idea that light is a particle. So that's important. So you should understand from the photoelectric effect that the kinetic energy of an electron depends not on the intensity of the incoming light, but rather the frequency. Okay, and there's an equation that shows that, and the equation is the following. The kinetic energy is equal to h times nu minus work function. And this defines what each of those variables are. So kinetic energy is the energy of an ejected electron. H, as we saw before, is Planck's constant. Nu, this is not V, represents frequency. And this nu symbol, which you may or may not have seen before, psi, represents the work function. So work function. And the work function, you can think of it as the minimum amount of energy required to cause an electron to get emitted. Okay, so we also call it threshold energy. You'll see it usually as work function though. Either this will be given or you'll be asked to calculate it. So an example of a problem you might see on your exam is the following. So it says a metal plate is illuminated with incident light of wavelength 4.16 times 10 to the negative 7 meters. They give you the work function. It's potassium, and it's 2.75 times 10 to the negative 19 joules. And then they want us to calculate the kinetic energy in joules of an emitted electron. So the first thing I would do is I would identify this question as a photoelectric effect problem, and I would write my equation, which is kinetic energy is equal to h nu minus work function. Now there's one thing that I notice here, right? Nowhere in the problem am I given frequency, nu. I'm given wavelength instead, right? But you should remember that from wavelength, you can calculate frequency and vice versa. And to do that, you use the equation C is equal to lambda times nu, all right? And instead of writing nu, I can write nu, I can solve for nu, and nu equals C over lambda, all right? And so I can essentially replace nu with C over lambda, and in doing so, I have all the variables I need to solve this problem. Right? So I just plug and chug, right? I know I'm looking for kinetic energy, and I know everything else. So I have Planck's constant, which is my first variable, so that's just going to be 6.63 times 10 to the negative 34. That's going to be in joules times seconds. I multiply by the speed of light, which is c, that's 3 times 10 to the 8th meters per second. And then I divide that all by lambda, and that's the wavelength, so that's 4.16 times 10 to the negative 7 meters. And then I subtract by the work function, which is given to me as 2.75 times 10 to the negative 19 joules. All right? And then, of course, you put this in your calculator. You're always given a calculator on your exam, whether it's quiz, final, midterm, and you should get 2.03 times 10 to the negative 19 joules. And the reason I use 3 sig figs in my answer is because I was given 3 sig figs in the problem. So that's the kinetic energy of an emitted electron. It's the kinetic energy per electron. per photoelectron. So let's try the next example. Next example says electromagnetic radiation of this wavelength, 2.94 times 10 to the negative 7 meters, ejects photoelectrons at this kinetic energy. When incident on a clean metal surface, calculate the work function. So now it's asking us to calculate not the kinetic energy, but the work function. Same thing as before. We're going to start with that same formula, which is kinetic energy is equal to h nu minus work function, right? General rule of thumb is whenever you have a problem, write the equation associated with that topic, okay? And then you can figure out where to go from. So here we're looking for lambda, right? So I can write, excuse me, not lambda, we're given the wavelength, we're looking for the work function, psi. So we can write in terms of work function, right? If I move it over, that gets us h nu minus kinetic energy. And here I'm not given frequency, so I can do the same thing as I did before. I can replace nu with c over lambda. So hc over lambda minus kinetic energy, and now I have everything I need to solve, right? So I just plug and chug. So the work function is equal to 6.63 times 10 to the negative 34 joules times seconds. That's Planck's constant, times the speed of light, which is 3 times 10 to the 8th meters per second, over lambda, which is our wavelength, 2.94 times 10 to the negative 7 meters, minus the kinetic energy, which is given to us above, 3.24 times 10 to the negative 19 joules. Put everything in your calculator, press enter, and you should get a final value of 3.53 times 10 to the negative 19 joules.